Yeah, if you remember, we talked about, I showed you what we call a cloud chamber photograph, where a particle comes and makes more and more particles. Okay, and the exact process involved, I think, let us not worry too much for the moment. But the same thing happens in air also. Particle comes in the atmosphere, top atmosphere, it hits the nitrogen nucleus, and lots of particles are formed. So the left-hand part, you can see like here, the x-axis is what we call it's actually atmospheric thickness. That means at the top of atmosphere it's 0, at sea level it is something like here it's 20 or something like that. All you have to see really is that it makes a lot of particles, it goes up, and it means the particles are formed, and then they are getting attenuated because nothing else happens. Particles are very creative to the left part, and then right part they are kind of dying off. This is what we call an extensive air shower, and this method is very important in very high energy astrophysics, as we will see. And this is what cosmic rays do in the atmosphere. The next one, which these are typically the type of arrays and experiments which we use to detect cosmic rays. This is for the left part, left hand side. You can see what's called an extensive wave shower. As I told you, this is how it probably looks. It's just a cartoon, and so you got a lot of scintillators on the ground looking. This is, for example, in Tibet, which is this is a Chinese-Japanese collaboration. You see lots and lots of plastics, what you call scintillators. So cosmic rays particles come and get recorded here. This is the one below is what is in Ooty in the south, in the near Coimbatore. Ooty, of course, you probably know, is a famous hill station. And again, similar experiment. So these are typical cosmic ray experiments, which are now which are still functioning. And the highest energy is just a kind of, it's not just an academic curiosity, but it's quite interesting. But all I would like to tell you is this is where the highest energy particles end, kind of. Our cosmic ray spectrum seems to end around 10 to the power of 19 for various reasons. One is because I think there is a mix up there on that. But anyway, so this is a graph showing that there are no more particles. And it's not that the sources cannot make, but something happens between when they make and when they come down to earth. So the next one is just a plot here with the right hand side. How the question we asked is what type of sources can make these particles. As I told you, they are very very high energy. So they are here is, for example, magnetic field strength. This is the size. So you got to be very small and a very high magnetic field, or you got to be very very big and even low magnetic field will do. This is what our understanding today is. This is how high energy processes are possible. Okay. So this is the thing, like 10 to the power 20 can come from neutron stars or come from huge galaxies. Okay, now another method to look at if you have a lot of money, as the Europeans are doing now, is put a satellite in space called USO. Now they're going to be coming up in the next 1 or 2 years. Is you look at the whole particle, the whole air shower. As you can see, it grows up and kind of dies down. This is what people are going to be doing. Okay, there's just an interesting aside that cosmic ray has also an interesting effect on climate, and essentially cosmic rays form kind of seeds for clouds, and now at high solar activity, what may happen is these particles, cosmic rays are less because they're kind of wiped away, not wiped away, they're swept away rather, and some people are trying to relate that to for example, the climate change and all that. But I think this is a very interesting aspect of cosmic rays. I won't dwell upon, but you please look into it. I think it has a lot of scope for studies there. Okay, now we are charged particles you have already done. And so now the next slide, next thing I'm going to go into actual more traditional astronomy, this is photon astronomy. Okay, we talked about charge. Now let us just look at timelines now. Now there is only optical astronomy for a long time. Till 1930s, Neil Jansky came and he started radio astronomy. Even in optical astronomy, the things are different once Galileo came on the scene. But it's only in the 1960s, about 50 years ago, this high energy astronomy started. But as I showed you in probably the third or fourth slide, that one of the reasons it could not happen was because we needed to go up in space, and we needed to go above atmosphere. and we could that way the rockets and things like that started. So that's how X-ray astronomy, etc., started late 60s, mid 60s. Now this is just one picture. Actually, I would have liked to talk about X-ray astronomy, but I don't have much time. I'm sure it has been covered before, and these are the two pioneers. But you just see on the left again, this multi-wavelength aspect keeps coming all the time. Now you can see what the Chandra satellite doing X-rays, and this is the Gamma ray satellite, which used to be called CGRO, Hubble, and then that's the infrared time thing. As I said, we won't talk about X-rays, but some processes which make X-rays also make gamma rays. So that's where X-ray and gamma rays have kind of a cousin type of a relationship. And as we know, but to make high energy particles, you need a lot of temperature. But we have that type of temperature. We do not. As in the formula here indicates the Stefan's law type of thing. It indicates it's not possible. So we need very high energy particles, relativistic particles. So this aspect of astronomy, we also call it non-thermal. Okay, this thermal means, for example, fusion is a thermal thing, but this is non-thermal. So these both X-rays and gamma rays are non-thermal things. Now we come to gamma ray astronomy, which actually is supposed to be my the main thing. And you can see on the right why if you read it a little more carefully, why they are interesting. This I've been telling you all the time, but they said in so many words that because all these very interesting objects like crab, for example, this Cassiopeia, which is the brightest radio source, is shown on the left there, and so all these are maybe high energy particles, but we don't know a lot about these things. This is active galactic nuclei, as I showed you already. That is you can concentrate on that and see why it is important. But I have already said it so many slides. How do we do gamma ray astronomy? Which is now gamma ray astronomy is now as I said, it's a photon astronomy now, and the methods are very different, and it all depends on, for example, uh, uh, the energy range you are in, because at different energies, different processes become important. Now, you please concentrate on this slide here. In the middle, we show the lowest region called the low energy astronomy, low energy gamma ray, 0.1 to 10 GeV. And I'll show you the next slide how it's done. It's a simple pair production thing. And you put a detector, and the gamma ray comes and makes electron protons, sorry, positrons. Okay, that is what is done even today in satellites. And the next one, the left part now, is what is called the atmospheric Cherenkov method, on which I will talk more and more later slowly. And this is again what happens in atmosphere is a shower of particles produced, by now as you know very well. But the shower itself is not important. Actually, these particles make Cherenkov radiation. They go on making Cherenkov radiation, as you will see, and you put some detectors there, and you try to determine the gamma ray detection, etc. And at the very high energy, this is a typical cosmic ray. I've already shown you how cosmic ray experiments are done with scintillators and all that. So these are the three energy regions. The middle one is called low energy, but better, we don't have other words here. The other one is medium energy, and this is near about 100 GeV now, I'll show you. And this is much later at about 100 GeV. And that's a typical age hour. By now you must be familiar with that.